for efficient transfer.
Right.
Instead of sending the entire file every time there's a change,
Right.
you only send the modified chunks.
That saves bandwidth and speeds up syncing.
Exactly.
It's like sending a patch instead of the entire software program every time there's an update.
Exactly. And then there's the challenge of handling conflicts.
Right.
When multiple users edit the same file simultaneously.
That's a classic problem.
Yeah. How do you make sure everyone's changes are saved
Right.
without creating a Frankensteinian document?
Exactly.
The book suggests techniques like optimistic locking
Okay.
and conflict resolution algorithms.
Right.
Optimistic locking assumes that conflicts are rare
Okay.
and only checks for them at the time of saving.
Right.
If a conflict is detected,
Yeah.
it provides mechanisms for users to resolve it,
Right.
like choosing which version to keep or merging the changes.
So it's about being prepared for those conflicts, but
Yeah.
not letting them bog down the system.
And metadata caching is crucial here.
Okay.
We want to keep track of file name sizes, modification times, all that.
Yeah.
But we don't want to be hitting the server for that info every time.
Right.
So cache it locally on the user's device for fast access.
Okay, so we've covered file storage syncing and conflict resolution. I'm ready to jump into the world of real-time communication with chat apps.
This is where things get really dynamic.
Right.
We're no longer dealing with those simple requests and responses.
Right.
We need persistent connections between users and the server
Right.
for instant messaging.
So how do we achieve that?
Yeah.
I remember the book mentioning WebSockets
Yes.
and long polling as two popular approaches.
Right. WebSockets are the more modern solution.
Okay.
They allow for bidirectional full duplex communication
Right.
over a single TCP connection.
So less overhead and lower latency compared to long polling,
Exactly.
which relies on repeated HTTP requests.
Yeah, it's like having a dedicated phone line versus constantly redialing.
Exactly.
And the book also delves into message delivery and acknowledgments.
Right.
We need to make sure those messages get where they need to go.
Yeah.
Even if there are network hiccups or server restarts.
Yeah, reliability is paramount.
Yes.
Imagine if those messages just vanished into the ether.
And of course, scaling is a huge concern.
Right.
We need a system that can handle millions of users chatting simultaneously.
Right.
That's where message queues and distributed caching become essential.
So a message queue acts like a holding area for those messages,
Yeah.
ensuring they get delivered even if the recipient is temporarily offline.
Exactly.
And distributed caching helps us store frequently accessed data
Yeah.
closer to users, reducing latency.
Exactly. The book provides a great overview of different message queuing systems like RabbitMQ and Kafka,
Okay.
and how to choose the right one for your needs.
Okay, we've covered a lot of ground,
We have.
but we're just getting started.
Yes.
Next, we'll revisit Twitter, going deeper into its architecture,
Okay.
and then explore the world of video with YouTube.
Get ready.
All right.
We'll be tackling massive data complex algorithms and all the challenges that come with building systems that operate at a global scale.
Okay, so we're back and ready to tackle some of the heavy hitters in the system design world.
All right, let's do it.
First up, we're revisiting Twitter. But this time, we're going deep into the architecture that supports its massive scale
Right.
and, that constant flood of new content.
Yeah, this chapter really showcases how to build a system that can handle hundreds of millions of users,
Yeah,
billions of tweets, and that never-ending stream of new content.
right.
It's a masterclass in designing for scale and high availability.
And one of the first challenges that jumps out is how to efficiently store all those tweets.
Yeah.
I imagine a single database just wouldn't cut it.
Exactly. The book suggests using a combination of relational databases and NoSQL stores.
Okay.
Each type is optimized for different kinds of data and access patterns.
So maybe using a relational database for user information
Yeah.
and tweet metadata,
Uh-huh.
but then using a NoSQL store like Cassandra for the actual tweet content.
Yep.
Which is more write-heavy and needs to be super scalable.
Yeah,
Yeah.
you got it.
Yeah.
And then there's the challenge of generating user timelines efficiently.
Yeah.
Imagine fetching all the tweets from everyone a user follows every time they open the app. It would cripple the
It would be a huge bottleneck.
Yeah, the book mentions pre-generating timelines, similar to what we saw with Instagram.
Right.
But with Twitter, you've got retweets and replies to factor in.
Right. So you need to update those timelines in real time
Yes.
as new tweets, retweets, and replies come in.
Exactly. That's where message queues and background workers come into play.
So when a user posts a new tweet,
Yeah.
it gets added to a message queue.
Uh-huh.
Then a background worker processes it,
Right.
updating all the relevant timelines.
That keeps the main system humming along smoothly
Right.
and prevents those timeline updates from bogging things down.
Okay,
Yeah.
exactly. And of course, caching is essential here.
Yes.
Store those frequently accessed timelines in memory so they can be retrieved in a snap.
100%. It's all about optimizing for speed and responsiveness.
The book also touched on handling trending topics and notifications,
Yeah.
both of which, add their own layer of complexity.
Yeah. Trending topics involve analyzing the stream of tweets in real time
Right.
to identify those hashtags and keywords that are suddenly exploding in popularity.
Right.
This often uses algorithms like the top K problem, which
Mhm.
we've discussed in previous deep dives.
And notifications are another beast altogether.
Yes.
You need to deliver those real-time alerts to users when someone they follow posts, retweets them,
Yeah.
or mentions them in a reply.
This chapter really shows the power of distributed systems
Yeah.
and how all those different components work together to create a seamless experience for the user.
Okay, ready to step up the data challenge?
I think so.
Let's talk YouTube,
Okay.
a platform that has to handle an absolute deluge of video data.
This one is all about scale
And
and the
yeah.
unique challenges of working with video.
Yeah.
First off, those video files are huge.
Yeah,
We're talking gigabytes, potentially terabytes for a single video.
right. Storage becomes a mammoth task.
Yes, you need a system that can handle petabytes, even exabytes of data.
Right.
And you need to be able to retrieve those videos quickly.
Nobody wants to wait an eternity for a video to load.
Exactly. The book talks about using a distributed file system
Yeah.
like HDFS or S3 to store those video files across multiple servers.
Okay, and then you've got the issue of encoding.
Right.
You wouldn't want to store just one massive video file that everyone has to download,
Yeah,
regardless of their internet connection or device capabilities.
exactly. You need to encode those videos into multiple formats and resolutions
Yeah.
to cater to different bandwidths and screen sizes.
So the book suggests using a transcoding service that chugs away in the background,
Yeah.
processing those newly uploaded videos and generating those different versions.
Smart. And let's not forget about searching and browsing for
Right.
those billions of videos.
Yeah, you can't just rely on the title and description.
Right.
You need to be able to search the actual video content.
Yeah, that sounds incredibly complex.
It does.
How do you even begin to index the content of a video?
Right.
The book mentions techniques like speech recognition and optical character recognition to extract text from the video's audio and visuals,
Wow.
making it searchable. It's amazing how those technologies can be applied
Yeah.
to unlock the content within a video.
And caching is essential here, right?
Yes.
You want those popular videos readily available
Yeah.
on CDNs around the world
Uh-huh.
so they can be delivered to users instantly, regardless of location.
This chapter is a great example of how multiple layers of optimization are needed
Yeah.
to create that smooth, responsive user experience we expect from a platform like YouTube.
Okay, let's shift gears to something we use every single day without even realizing it.
Okay.
Type head search,
Ah, yes, those autocomplete suggestions that magically appear as we type.
right?
It seems so simple,
Yeah.
but designing a system to handle billions of searches and provide instant suggestions
Right.
is a real feat.
It is.
The book delves into using a data structure called a trie
Okay.
to store those search terms and their frequencies.
Right.
Each node in the trie represents a character, and by traversing the trie, you can quickly find all the words that start with a given prefix.
So if I type cis,
Yeah.
the trie would guide me to all the words that begin with cis,
Yep.
like system, systematic, and so on.
Exactly. And by storing those search counts at each node,
Right.
you can easily figure out the most popular suggestions.
But keeping those suggestions up to date as people search for new things
Yeah,
presents a challenge, right?
it does.
You can't be updating the trie in real time with every single search.
That would create a huge performance bottleneck.
Right.
The book suggests using offline processing to update the trie periodically.
Oh, okay.
You'll log those new searches and their frequencies, and then at set intervals, you process those logs and update the trie accordingly.
That's a clever way to balance real-time updates with system performance.
Yeah, you get the best of both worlds.
You do.
And, of course, scaling is a factor.
Right.
We can partition the trie across multiple servers, each handling a subset of search terms. The book also mentions using techniques like Bloom filters
Right.
to quickly check if a term exists in the trie
Right.
before even querying the server.
It's amazing how much optimization goes into something that feels so effortless to the user.
Yeah, it really is.
Okay, let's move on to a crucial but often overlooked component,
Yeah.
API rate limiters.
Yes. These are the unsung heroes that protect our services from abuse.
Right. It's all about preventing bad actors from flooding our systems with requests.
Yeah.
And potentially bringing them down.
And I remember the book covering different algorithms like fixed window,
Right.
sliding window, and token bucket.
Fixed window is the simplest.
Yeah. You set a limit on the number of requests a user can make within a specific time window.
Right, like 100 requests per minute.
Exactly.
But I recall that fixed window has some limitations, right?
It does.
What if a user blasts all 100 requests at the beginning of the minute?
Yeah.
They'd be locked out for the rest of that minute,
Right.
even if their usage is legitimate.
Exactly. Sliding window is a bit more sophisticated.
Okay.
It tracks requests over a sliding time window,
Okay.
allowing for some flexibility in how those requests are distributed.
Okay, and token bucket is even more flexible, right?
Yes.
It's like having a bucket that gets filled with tokens at a constant rate.
Mm-hmm.
And each request consumes a token.
Yep.
If the bucket is empty, the request is rejected.
Right.
This allows for bursts of activity while still enforcing an overall rate limit.
That's a great way to visualize it.
Right.
The book also covers how data structures like hash tables and sorted sets can be used to efficiently implement these algorithms.
This chapter really dives into the nuts and bolts of building a robust and scalable rate limiter that can handle massive traffic while keeping those malicious actors at bay.
Okay, let's switch gears and talk about the silent workhorses of the internet.
Okay.
Web crawlers.
These bots are constantly scouring the web, indexing content and making it searchable.
Designing a web crawler presents a unique challenge.
Right.
You need to navigate the vast and ever-changing landscape of the web, handle all sorts of content, and most importantly, be respectful of the websites you're visiting.
Right. We don't want to be labeled as spammers.
Exactly. The book breaks down a web crawler into its core components.
Okay.
The URL frontier, the HTTP fetcher, the extractor, the duplicate eliminator, and the data store.
Okay, so the URL frontier is like a to-do list of websites to crawl. The HTTP fetcher retrieves the web pages.
Right.
The extractor parses those pages and identifies new links to add to the frontier.
Yep.
The duplicate eliminator ensures we don't crawl the same page multiple times.
Exactly.
And the data store is where we store all the content we've collected.
You got it. The book also discusses handling robots.txt, which tells crawlers which parts of a website they're allowed to access, as well as dealing with different content types.
Yeah.
You might need to parse HTML, extract text from PDFs, or even process images and videos.
And, of course, being polite is key.
Yes.
We don't want to overload those web servers with too many requests and potentially cause problems.
This chapter really emphasizes designing for scale, efficiency, and respect when you're interacting with a constantly evolving entity like the web.
Okay, let's dive into another feature we all use daily, news feeds.
Okay.
Whether it's Facebook, Twitter, or Instagram.
Yeah.
We rely on those feeds to stay informed and connected.
Right.
But behind those seemingly simple streams of content lies a complex system.
Designing a newsfeed is a delicate balancing act.
Yeah.
You need to personalize those feeds for each user, showing them content they'll find relevant and engaging.
Yeah.
But you also have to handle a huge volume of real-time updates.
The book talked about pull-based and push-based approaches to feed generation.
Right.
With pull-based, the user's device periodically checks for new content, which can be inefficient and lead to delays.
Right, and with push-based, the server pushes new content to the user's device as soon as it becomes available.
Right.
Which is more real-time, but can be tricky to implement at scale.
Right. The book suggested a hybrid approach, combining the best of both worlds.
Exactly, and caching is vital here to avoid constantly regenerating those feeds from scratch.
And then there's ranking.
Right.
You can't just display everything chronologically.
Yeah, you need to prioritize content based on factors like recency, popularity, and the user's past interactions.
That's where machine learning can come in, right?
Exactly.
You can train models to predict what content a user is most likely to find interesting and personalize their feed accordingly.
It's a fascinating application of machine learning to create those engaging and addictive feeds we all know and love.
Okay, let's shift gears to Yelp.
Okay.
Finding those hidden gems and avoiding tourist traps relies on some clever system design working behind the scenes.
This chapter is all about location-based searches and making them lightning fast and relevant.
Yeah.
The book talks about using grids and quad trees to index geographic data.
So instead of searching every single location in your database, you can narrow it down to those places within a specific geographic region.
Right. And quad trees are especially useful for those non-uniformly distributed locations. Like in cities where you have dense clusters of businesses in certain areas.
Right. The book also covered efficiently handling search queries, ranking results based on proximity and popularity, and caching those frequently accessed locations for quicker retrieval.
It's all about optimizing those searches so users can find what they're looking for in a snap.
Now let's take everything we've learned from Yelp and apply it to building Uber.
This chapter takes those location-based search concepts and adds the element of real-time updates. We're no longer dealing with static locations like restaurants and shops. We have those little cars zipping around the map, constantly updating their positions.
That adds a whole new layer of complexity.
Yeah. How do you track those drivers in real time, match riders with nearby drivers efficiently, and keep everyone informed? The book suggests combining a few techniques we've already discussed. Grids or quad trees for location indexing, message queues for handling those real-time updates, and push notifications to communicate with riders and drivers.
It's a great example of how we can mix and match different system design patterns to tackle specific challenges.
Yeah, for sure.
And for our grand finale, let's design Ticketmaster, a system that has to cope with those massive spikes in traffic when millions of people are scrambling for concert or game tickets.
Talk about high stakes. You need a system that can handle that intense pressure and ensure fairness when it comes to those limited tickets.
This chapter is all about concurrency transactions. And preventing the dreaded double bookings where two people end up with tickets for the same seat.
The book mentioned using optimistic locking and pessimistic locking to ensure that only one person can book a specific seat at a time. And transactions are crucial here. We need to make sure that if a user selects multiple seats, either all of those seats are booked or none of them are.
No partial bookings allowed.
Exactly. And then there's the waiting list. What happens when a show is sold out but someone cancels their tickets? The book recommends a priority queue to manage those waiting users. So those who have been waiting the longest get first dibs on those newly available tickets.
It's all about fairness and transparency.
This chapter highlights the importance of database concepts like ACD properties, atomicity, consistency, isolation, and durability when handling sensitive data and financial transactions.
Wow, we've covered a ton of ground in this deep dive.
We have.
From those tiny URLs to massive video platforms, from autocomplete suggestions to ride-hailing services. We've explored the key concepts and design patterns that power the systems we use every single day.
It's amazing how much goes on behind the scenes.
It really is.
And all the things that we take for granted.
And remember, this is just the starting point. This deep dive has given you a solid foundation to build upon. Keep practicing, keep learning, and don't be afraid to get your hands dirty with those system design challenges.
And as the book reminds us, always keep the CIP theorem in mind. You can't have it all in a distributed system. You have to make choices and prioritize between consistency, availability, and partition tolerance. Think about those trade-offs and which aspects are most critical for the system you're designing.
So keep those system design muscles flexed. And you'll be well on your way to acing those interviews and building amazing systems.
Until next time, happy designing all